command, but we are looking for latency. So latency is from a god. So we must, as I told you, the development company wants to have very, very little latency environment. This is to be known, the chart, how the difference between the NFS and KNFS. We see that there is bypass OS caches, kernel caches, there's not so much layers that is direct to storage. So improvement was great on those times, which was designed the NFS. But back to our hardware part. How to build our InfiniBand network. It's very simple, just few cards, post-channel adapters, InfiniBand switches, or Ethernet. It depends on the specification, because you can have RDMA enabled on Ethernet layer, it's called HrOUG, or InfiniBand. So it depends on you, and depends on the hardware. These switches mostly can do, it depends of course of the license, can do Ethernet and InfiniBand. It's a DPI license, called a DPI license. And additional fiber or copper cards, nothing sophisticated, truly. Software part is even easier. You have software developed by Open Public Alliance, and this software is delivered to Windows, Linux, and FreeBSD. Also, OpenBSD is part of now of this implementation. I wrote about Mellanox because it's very important. So most of the infrastructure is by Mellanox. So Open version developed by Mellanox from version 3.3 plus, it's not supported in the NFS over RDME. I'm writing this on this slide because it's very important, and Mellanox don't tell this information. I don't know why. Even in changes log, there is no information about this. That's not supported. So we are using standard offset 2.0 from the public repository from HrOUG Enterprise Linux. The system which you will choose, it depends on you, of course, should be supported by HrOUG. So I don't know, CentOS, HrOUG Enterprise Linux, that depends on you. This is the installation. Just 3 simple steps without any problem. You install InfiniBand support on the client and server side. You share mode to export, remote probe as per HDMA. This is not for now mandatory because it's difficult from the version of HrOUG Enterprise Linux 7.2. It's difficult, but I added this information. We run NFS server, add RDMA to port list, and it's done on the server side. It's working. On this, as you can see on client side, it's even easier. Just mount with option, with RDMA option. I added also this slide too because many people ask me on the groups why RDMA, NFS RDMA is not working. So the first step we must to check if in our RDMA it's working. So this is free utilities we can use to check if our RDMA is working. It's the first step of the troubleshooting. So I added this to be the first step of the troubleshooting. If it's working, we go to NFS and checking what's going on with NFS. Okay, so most important thing, let's test it, because we can talk, theory, but let's test the real performance. This was my very simple test environment. Simple Mellanox DPI switch, Netgear switch, which was 10 gigs, and 2 servers. Servers depends on you. 2 cards, Connect X3, so rather old card, 56 gigabits. 1 10 gigabits standard TCP/IP card, and Samsung consumer disk. This is very important. Why I add this not so great performance NVMe disk? Because I can choose, I don't know, enterprise NVMe disk and test it. But we must remember about the bandwidth of TCP/IP. The bandwidth is 10 gigs. And today, this enterprise disk and NVMe disk can do 4, 5, even 6. It depends on the Samsung can do a 6 gigabytes per second. So the bandwidth was very interesting. And I don't want to test the performance of the disk, but the performance of the transportation layer, not the disk. So the disk was rather low speed. It's consumer, not even pro version. As you can see, software environment or enterprise Linux 7.4 kernel version. This is very important. I will show you why I use this kernel version, because it's not related to the NFS over VMI. It's related to my measure utilities. I will show you why. And of course, TCP/IP, the NFS tuning option was added. I do not add slides about tuning the NFS. If you would like to see how we should tune the NFS, there is great presentation from our colleague Marcin Kupirowski, who is at session at the same time session. This is the paper you can download and check. Or investigation done by Marcin. It was great paper, so you can read it. This is my measure utilities. eBPF. It's based on BPF. Let's say in the shortcut that it's something like new dtrace. It is maintained by main guy who is maintaining it, Brendan Rick. I don't know if somebody knows who is Brendan Rick. Yeah, you should. So Brendan Rick is involved in this project, and it's truly great tool. For me, much more easier to write the probes than for dtrace, for example. A lot of possibility to write in Python, C, whatever you want. Okay, but we are talking. Let's check our tests. The most important one is this red lines. Two red lines. This is standard field testing with NFS over DMA. We can test latency, and we must know that the performance from the I/O subsystem, from the OS subsystem using this pure tests will be different than from I don't know, slope or something like that. But I would like to show you the difference between this implementation on the operating software layer. So we can see that it's 3.7 milliseconds, the latency, and the bandwidth is 1.6 gigabytes per second. So it's not bad. This is the standard TCP/IP. The same disk, only the transportation layer was different. The difference is huge. Latency is 5.5, and bandwidth is 1 gigabytes per second. The difference is very big. This is simple distribution which I show you from this eBPF software. So you can see this CPU latency. Of course, it's microseconds. It's latency on CPU, waiting on CPU. So you can see that this latency on the standard kernel NFS server is much more higher. So this is why overall latency of the I/O subsystem is higher. We can also check NFS latency for read operation. This is also much more higher latency for this usage. I/O wait histogram. This was the output from after the slot test. Just simple query